I'm now absolutely delighted to be joined by Professor Yasumasa Nishiura. Professor, welcome.
Good morning.
Thank you very much indeed for taking the time to talk to us today.
My pleasure to be here.
Now you're going to be talking to the conference on Wednesday about collision dynamics, I believe. What will you be talking about on Wednesday?
First of all, the collision is about moving localized patterns. This is ubiquitous. You can observe this kind of object in some chemical reactions and action potential in nervous tissue and granular dynamics, or even vegetation or droplet on some liquids. So if you have some inhomogeneity, some chemical activity is very high or some concentration is very high, then you may regard these are localized moving objects. So it's unavoidable to observe the collisions.
So what about the mathematical challenges that you face when you observe these collisions?
Okay, so because it is localized, spatial, so you can distinguish internal and external. So there is an interaction between internal dynamics and external dynamics. And through this interplay, these two dynamics, these localized moving objects undergo, for instance, large deformation. When they collide strongly, they may change. They may fuse into one body, or they may annihilate each other. So that this kind of strong collision always associated with large deformations of dynamics and change, sort of a Bayesian switch of the dynamics from one state to another. But from mathematical point of view, this kind of transient dynamics or the large deformation is very hard to describe, and just the conventional mathematical tools, except the numerical approach, is very weak, not so strong enough to understand all the details.
Your work has broader application, hasn't it? A broader organic application. Tell us about that.
Localized pattern has an interface. An interface is always important, especially in biological applications. So each cell has an interface, and that's the kind of important part, communication between internal and external. And I have my approach has a great potential if you want to apply the method to the biological questions. For instance, I plan to give a talk about the behavior of the amoeba. And you put the amoeba in a simplest case, one-dimensional lane, and then you put some toxic materials in the middle. And the question is how they behave, how they change their behaviors when they encounter such a toxic area. So they don't like this space. So they just turn back, or they try to penetrate, or how they do that. That's the question. Of course, if you look at this problem microscopically, it's really complicated. Just sensing the outer world, it's a very, very complicated chemical reaction occurs. So that I just, from top-down manner, cook up some very simple mathematical model. And through this analyzing this mathematical, we can somehow understand sort of diversity of behaviors of this what is called physical, the name of the amoeba, how they respond to the change of the external world.
Professor, thank you very much indeed for joining us. I'm sure your talk will go extremely well on Wednesday, and thank you once again.
Thank you very much.